Okay, let's just jump right into this because the core problem we're tackling today is uh, it's both completely obvious and at the same time really surprising.
Hmm.
When you look at a heavy-duty vocational vehicle, I mean a massive cement mixer, you just naturally assume the biggest drain on its efficiency is the drive,
Yeah.
right?
The long haul, the acceleration, fighting gravity.
Exactly. But the raw operational data, it tells a completely different story.
It absolutely does.
Mhm.
And that's the crux of it. The most massive hitter inefficiency, the biggest waste of fuel, it doesn't happen when the truck is moving at all.
Right. It happens when it's standing still.
Exactly. It happens when the truck is completely stationary. The analysis shows that these mixers spend, and this is an incredible number, somewhere between 40 and 60% of their operational life just idling,
Idling, just sitting there.
just sitting there, running that huge diesel engine for one reason and one reason only, to power a hydraulic pump that keeps the drum rotating.
Which is a non-negotiable. You have to do it. If that drum stops spinning, the concrete sets.
And the truck is basically a write-off. So
Yeah.
you have this massive engine burning fuel just to do a job that really it's not designed for.
It's an environmental contradiction, and it's a huge economic drain. So our deep dive today is all about the engineering solution to that
But
problem.
a really revolutionary one.
It is. We're talking about the strategic shift of these heavy-duty mixers from that traditional diesel hydraulic system to a really sophisticated P2 hybrid architecture, which is then coupled with a dedicated electric power takeoff system, the ePTO.
And that transition is, it's fundamentally a move away from mechanical systems defined by brute force
Right.
to intelligent systems that are governed by software and, crucially, high voltage electricity.
Yeah.
This forces us to manage an extremely complex dual voltage environment.
So you have two systems running in parallel.
You do. You have the familiar 24-volt control logic network, which is like the brains, managing the sheer power of the 400-volt high-voltage drive system, which is the muscle. It's an integration problem of the highest order.
So our mission for you, the listener, today is to adopt the mindset of a top-tier engineering consultancy. Think McKinsey, AVL, Ricardo. We've been tasked with implementing this shift globally.
Right.
We're going to define the entire technical roadmap, focusing specifically on the testing, the verification, and the regulatory certification framework that you need to bring this new generation of intelligent, efficient mixers to market all over the world.
And we'll get into the key engineering deliverables, the actual documents that prove safety and compliance.
Because the central engineering challenge here is so unique, even within the EV space, I mean, how do you guarantee the safety and the durability of complex power electronics?
Your motors, your inverters, your battery packs.
When you're subjecting them to constant high vibration, extreme temperature swings, and the daily assault of, concrete slurry and high pressure water washing.
The answer is meticulous, almost obsessive adherence to the V-model validation cycle. You have to follow the process from a purely abstract mathematical model all the way through to the final stamp of approval on a compliance check. There are no shortcuts.
All right, so let's start with that strategic foundation. Part one, the P2 hybrid and the ePTO advantage.
Do it.
For our listener, the key here is understanding the P2 positioning. We know the P stands for position, but why is position 2, that spot between the engine and the transmission? Why is it so versatile for these heavy-duty, high-torque applications?
P2 really is the sweet spot for vocational and heavy-duty vehicles. And it's precisely because of its structural placement.
Okay.
You have the electric motor literally sandwiched between the combustion engine, the ICE, and the conventional transmission. This layout lets the system share the existing driveline components, which is a huge cost saving, while also offering multiple operational states that are just critical for efficiency.
And the physical component that enables all that versatility is something called the K0 disconnect clutch.
Absolutely. The K0 clutch is the hero component here. It's the critical mechanical element that facilitates the decoupling of the two power sources.
So when that clutch is closed or engaged,
The electric motor and the diesel engine are locked together. They operate as one unit. This allows the motor to provide that instantaneous torque assist, we often call it torque fill, during transient phases.
like gear shifts.
Exactly. During a gear shift, there is a momentary drop in power. The electric motor fills that gap perfectly, smoothing out the acceleration and reducing the load on the diesel. The goal is always to keep the ICE in its most efficient operating zone for as long as possible.
But the real magic, as you said, happens when that clutch is opened, disengaged. That's when the electric motor gets to really be independent.
Precisely. When the K0 clutch is disengaged, the whole game changes. The vehicle can now operate in a pure electric mode, EV mode, at low speeds. Think navigating a depot or creeping around a quiet urban job site.
And regenerative braking.
And this is huge. During deceleration, the system can maximize regenerative braking. A cement mixer is a massive vehicle with huge kinetic energy. By separating the heavy, high-friction diesel engine from the electric motor, the system recaptures so much more of that energy without the parasitic drag of the ICE trying to slow it down.
Okay, but that K0 clutch, it sounds like a major point of failure. I mean, you've got constant coupling and decoupling under immense torque on a high-vibration construction site. How do engineers even begin to guarantee its longevity and its isolation?
That's a fantastic question, and it's a critical challenge we address directly in the DVP&R, the validation cycle we'll talk about later. That K0 clutch mechanism, it has to be rated for hundreds of thousands of engagement cycles under maximum engine torque.
That's incredible.
It often requires specific material treatments, things like plasma nitride coatings, just to handle the high-friction, high-heat environment. And beyond the hardware, the control logic in the supervisory control unit, the SCU, has to be perfect. It has to carefully manage the engagement and disengagement speeds to minimize torque shock and extend its life.
Okay, now let's get to the innovation that really solves that initial problem we talked about, the idling. The ePTO, the electric power takeoff. This is the paradigm shift.
The ePTO system is the defining factor for this whole application. Traditionally, the drum's rotation was tied to a hydraulic pump, which was driven directly by the diesel engine's RPM.
So engine speed dictated drum speed.
Exactly. And it was often very inefficiently controlled. With the ePTO, the electric motor driving the drum gets its power directly from the 400-volt battery pack. It completely decouples the upper structure's operation from the chassis powertrain.
So the system achieves that transformative stop-and-mix capability.
Yes, that's the key phrase. The driver arrives on site, engages the park brake, and immediately shuts down the noisy, polluting diesel engine.
And the drum just keeps turning.
The electric motor continues to rotate the drum at a constant, precisely regulated speed, usually about 2 to 6 RPM, just enough to prevent the concrete from segregating.
And that's where the fuel savings come from.
That capability is the direct source of those 25 to 30% fuel savings you see in typical duty cycles. It's almost all from eliminating diesel idling for mixing. And it's the only way to meet those strict urban noise and emissions regulations.
Okay, that efficiency gain immediately pushes us into the complexities of the dual voltage environment. The industry seems to have landed on 400 volts for the high-power system, not the, cutting-edge 800-volt architecture we see in some premium passenger cars. What's the strategic reason for sticking with 400V here?
It's a very pragmatic choice. It's rooted in optimizing the total cost of ownership, the TCO, and leveraging the incredibly mature commercial vehicle supply chain.
So it's about reliability and availability.
It is. 400-volt technology is well established for heavy-duty components. It perfectly balances the need for high-power delivery and managing line losses without the massive component cost and complexity you'd need for 800V.
But 800V is better for fast charging, right?
It is. It excels at enabling ultra-fast charging for long-range passenger cars. But a vocational truck's duty cycle is completely different. They charge overnight in the depot. They don't need a 10-minute turnaround. So for us, 400V gives us the best combination of robust components, established safety procedures, and cost efficiency for the power we need. 80 to 120 kilowatts for propulsion and maybe 40 to 50 for the drum rotation.
So the 400-volt system handles all the muscle, the P2 propulsion and the ePTO drum drive. That leaves the 24-volt network, the system everyone is familiar with, to handle the brains.
Exactly. The 24-volt network acts as this highly reliable nervous system and supervisory control layer. It powers the supervisory control unit, the SCU, which is the master vehicle controller.
And the SCU is making all the decisions.
Constantly. It's a complex piece of hardware that's always analyzing dozens of inputs: battery state of charge, engine RPM, driver demand, drum speed, to execute the energy management strategy. It decides the optimal power split, it coordinates the K0 clutch, and it manages all the safety redundancy, including that critical low-voltage, high-voltage interlock loop.
So for that system, reliability is everything.
Reliability and instantaneous response are key, which is why we rely on the established, proven 24-volt architecture. You don't innovate on your safety-critical control layer if you don't have to.
So the final piece of this strategic puzzle is really quantifying the replacement of the old hydraulics. We're swapping out physical pumps and hoses for these high-precision electric motors. What specific gain does a permanent magnet synchronous motor, a PMSM, bring that hydraulics just can't match?
The PMSM is a complete game changer. Hydraulic systems, they're robust, but they are inherently inefficient. They lose a tremendous amount of energy to heat and friction as fluid gets pumped around.
Yeah.
You're often looking at efficiencies below 60%.
Wow.
PMSMs, on the other hand, boast peak efficiencies that often exceed 95%.
That's a huge difference.
It's massive. And beyond just the raw efficiency, the PMSM offers exceptional torque density and, crucially, superior control fidelity. A hydraulic motor might be fine for brute force mixing, but the PMSM allows for precise dynamic torque control.
And that's essential for the more advanced functions.
It is. It's what enables things like the digital slump meter and the rapid oscillations you need for rocking logic, which we'll get into. It fundamentally shifts the truck's operation from energy-wasteful mechanics to highly optimized electromechanical control.
Okay, so once that architecture is defined, we enter what has to be the most critical phase of product introduction: validation, following the V model.
That's right.
And we start at the very top of the V, the abstract, defining the system's intelligence before any hardware is even assembled. So let's focus first on those early stages: model in the loop, EMI-L, and software in the loop, SIL.
This virtual phase is, it's where the core competitive advantage of the hybrid mixer is really established.
Yeah.
And it's where we realize massive cost savings by debugging things super early.
So what is model in the loop?
In the EMI-L phase, we're using specialized tools, things like AVL Boost or Ricardo Wave, to create a purely mathematical model of the entire powertrain.
So this is all just code, no hardware.
Purely code. The engine thermodynamics, the transmission gear ratios, the battery discharge curves, the motor performance maps, it's all a simulation.
And what's the ultimate goal of that initial MIL phase?
It's all about calculating the optimal power split. The SEU's brain, its energy management strategy, or EMS, is tested against these mathematical models to define precisely when the P2 electric motor should step in and help the diesel engine.
All to keep the engine that sweet spot.
Exactly. To ensure the ICE operates strictly within its most efficient zone, maximizing fuel savings, while also hitting those strict tailpipe emission standards for NOx and CO2 that are mandated globally. We literally map out the most efficient way for the truck to behave in a simulation before we build anything.
Okay, now a cement mixer adds a very unique and highly volatile variable to this virtual world. How on earth do you accurately model the dynamics of the load itself, this fluid sloshing concrete?
This is the critical and often overlooked necessity. Standard vehicle dynamics modeling is not enough. You have to incorporate specialized simulation tools.
What kind of tools?
Typically something based on the discrete element method, or DEM. We use packages like EDEM. We are simulating the fluid dynamics of the concrete mix itself, the sloshing, the load migration, the effect of different aggregate sizes and water content.
Because that shifting mass has a huge impact on the vehicle.
A profound impact on the vehicle's roll stability during cornering and braking.
So the model needs to be able to tell the SCU, hey, the center of gravity just shifted laterally by 15 centimeters.
Exactly that. And the SCU, which we're defining in the next phase, it needs to be programmed to anticipate and react to that information. If the virtual model shows that an aggressive right turn with a very wet concrete mix leads to a critical roll angle,
The SCU can compensate.
the SCU can be calibrated to apply subtle regenerative braking to the outer wheels, or maybe adjust the ePTO torque to stabilize that movement. The entire dynamic behavior of the concrete has to be an integrated variable in that simulation loop.
So once that high-level strategy, the MIL, is optimized, we move to software in the loop, or SIL. This is where the actual production C code is introduced. What specific complex logic are we trying to verify here?
In SIL, we're verifying that the SCU's embedded software logic is robust and that it can execute these complex state machines flawlessly.
State machines.
The state machine just governs the sequencing of critical events. For example, the flawless transition from engine-off mixing mode back to hybrid propulsion mode when the driver decides to pull away from the site.
Which involves a lot of moving parts.
It involves coordinating the battery contactors, the motor controller, the transmission clutch, and the engine start signal, all within milliseconds. SIL is where we prove that sequence works every single time.
And this is also where we validate that crucial application-specific logic you mentioned earlier, the rocking logic.
Yes, rocking logic is a safety-critical, software-defined sequence. It's designed to prevent a catastrophic failure.
How so?
Well, if the concrete has been sitting for too long, or maybe the mixture is just too dry, the static friction can become so immense that the electric motor just can't overcome it.
You can't break it free.
Right. And if the driver just applies maximum torque, the motor will stall, leading to a potentially damaging overcurrent event. The rocking logic is programmed to analyze that initial torque request.
And if it's too high?
If it exceeds a predetermined threshold, it triggers this dynamic oscillation, a very rapid forward and reverse rocking of the drum to gently break that static friction. It saves the motor, and crucially, it saves the load from being lost and hardened inside the drum,
So you use SAL to make sure that complex sequence executes perfectly.
without conflicting with any other system safety protocols. It's a critical stress test for the software.
Okay, moving beyond pure software, we get to the really critical phase of hardware in the loop, or HIL testing. This is the ultimate test for the SCU hardware itself. Why do you call HIL the safe failure zone for high voltage architecture?
HIL is where the digital world finally meets the physical hardware, but in a totally controlled, non-destructive environment.
So what does that look like?
We connect the actual production SCU hardware to a high-fidelity, real-time simulator, usually a DSpace or SpeedGo platform. The simulator pretends to be the rest of the vehicle.
They fix all the signal.
It generates realistic electrical and sensor signals for the SCU, but it also allows us to inject faults that would instantly destroy a physical prototype or, worse, endanger personnel.
Okay, give us the deep technical detail on a really high-stakes fault injection that you have to do in HIL. Let's talk about validating the high-voltage interlock loop.
The HVIL validation is the central safety focus. It's non-negotiable. We'll simulate an insulation drop. That's a scenario where, say, vibration or wear has caused wire chafing, leading to a resistance drop between the 400-volt bus and the chassis.
Which is a very dangerous situation.
It creates the potential for lethal touch voltage. The SCU must instantaneously process this fault signal from the installation monitoring device, the IMD, and command the main contactors to open. In the HIL environment, we can precisely measure the time from fault detection to full de-energization.
And what are the time requirements for that shutdown? They have to be incredibly fast.
They are ruthlessly strict. The system has to reduce that residual 400-volt potential down to less than 60 volts DC within a maximum of 1,000 milliseconds.
1 second.
1 second. And often we target something much closer to 100 milliseconds in critical systems. We use the HIL environment to prove, over and over, that the system achieves this timing, even under conditions of high electromagnetic interference or network congestion.
And you can also test the physical loop itself.
Absolutely. We'll simulate the physical break of the HVIL's 24-volt loop, for instance, simulating a technician opening a maintenance cover while the system is energized. The contactors have to open immediately, relying on that dedicated low-voltage loop for total physical redundancy.
The SCU is also managing all this complex data, particularly on the J1939 CAN network. You have high-speed, multi-packet messages about battery health and motor state. How do you guarantee data integrity with all that high-frequency noise from the inverters?
That's where the high fidelity of the HIL platform becomes absolutely critical. The high-speed switching of the 400-volt inverter generates electrical transients, a lot of high-frequency noise.
So you need a simulator that can replicate that.
You need specialized HIL systems, often ones that incorporate field-programmable gate arrays, FPGAs, to accurately simulate the physical switching events, we're talking in the kilohertz range, to ensure that electrical noise doesn't corrupt the J1939 communication.
And you can inject faults there, too.
We inject communication faults, simulating lost packets or bit errors, to ensure the SU's error detection and recovery protocols work instantly, preventing a loss of power during a high-torque maneuver.
So finally, we move from the safety of the lab to full vehicle testing, the real-world grit that's required for the durability segment of the DVPNR. This is where theory meets high-vibration reality. What is the single most defining performance test that determines if this hybrid system is even commercially viable?
It is, without a doubt, the full load cold start.
Okay.
This is the ultimate test of the system's robust power delivery. We take a truck with a full 12 cubic meter drum, load it with concrete, and then let it sit overnight in a sub-zero environment. We're talking maybe down to minus 20 degrees Celsius.
So everything is freezing.
The water content in the concrete starts to freeze, the aggregate settles, and you create this monumental static friction on the drum's bearing surfaces.
And the electric motor has to deliver just an immense initial torque to break that solidified stack load free.
Precisely. The electric motor has to deliver peak starting torque, which can often be 3 times its continuous power rating, and it has to do it instantly.
And failure is not an option here.
Failure is not an option. If the system fails to rotate that drum, the load is ruined. The concrete will permanently set inside the drum.
Hmm.
And that's not just a lost batch of product. The truck is now out of service for days, while maintenance crews are in there with jackhammers manually chipping out hardened concrete. It's a multi-thousand-dollar maintenance event that takes the asset completely out of commission.
So passing that full-load cold start is the guarantee it's rugged enough.
It guarantees the system is ready for global operation, especially in colder climates.
The performance feedback from all these rugged tests then feeds directly into the final tuning phase, the SCU calibration loop. How does all that real-world data refine the system's intelligence?
The full vehicle tests provide this intense, complex duty cycle data that even the best virtual models can't perfectly replicate.
Right.
Engineers use this feedback to perform the final calibration and tuning of the SCU. A perfect example is refining the torque fill strategy. We can analyze the exact power dips during engine gear shifts under maximum load, and then tune the P2 motor's engagement parameters, its PID control sets, to perfectly smooth out that torque curve.
So it's not just about efficiency, it's about the feel.
It dramatically improves operator comfort and drivability, which is a huge selling point for fleet adoption.
And you mentioned using something called equivalent consumption minimization strategies, or ECMS. That sounds like a continuous optimization process.
ECMS is a critical advanced calibration technique. It means the SCU isn't just following a simple static map. It's constantly calculating the most economical blend of electric power versus diesel power based on its prediction of future demand.
So it's tailored to the specific job.
We calibrate the control parameters, the drum rotation speed, the target battery state of charge, to be optimal for the customer's actual job site profile, not just some standardized global test cycle like WLTP. By tailoring the SCU's brain to the specific needs of a construction site, we extract the maximum possible fuel savings.
All right, we've engineered the system, and we have proven that it works robustly. Now comes the non-negotiable gauntlet, regulatory certification.
The final boss.
When you fuse heavy machinery with 400 volts, safety standards are the ultimate legal authority. We have to start with a European benchmark, ECE R100, specifically Revision 3. What mandate in Rev 3 forced the most radical rethinking of battery pack design?
ECE R100 Revision 3 is the global gold standard for the safety of rechargeable electrical energy storage systems, or REESS. The absolute game changer is the thermal propagation requirement.
Okay, what is that?
The regulation acknowledges that high-energy density cells carry an inherent risk of internal short circuits, which can lead to thermal runaway,
Where one cell overheats and starts a chain reaction.
a chain reaction in the adjacent cells. The regulation mandates that the system must be able to detect a single-cell thermal event and, through sophisticated design, provide the driver with a minimum 5-minute warning signal before fire or explosion breaches the protective enclosure and enters the cabin.
5 minutes. That is the specified safety window for the driver and anyone on site to evacuate. So the battery pack isn't just an energy source, it has to be an engineered containment vessel.
That is the key shift. Meeting that 5-minute mandate requires engineers to integrate cell-level BMS sensing, not just pack-level monitoring, and use advanced material science.
What kind of materials?
We're talking fire-resistant materials, often ceramic blankets or specialized fire-retardant foams positioned between cell groups, and a dedicated venting system.
To channel the gases.
It has to safely redirect the high-pressure, high-temperature gas that's expelled during thermal runaway away from the cabin and the high-voltage connections without propagating the fire. This design work adds significant cost and complexity to the pack.
And R100 Rev 3 also mandates specific abuse tests that are highly relevant to our application, right?
Oh yes, Annex 9 of R100 details the mandatory abuse tests, which are crucial for construction vehicles. The pack has to survive physical assaults that mirror real-world stress.
Like vibration.
The vibration test, for instance, requires the battery to endure a specific sinusoidal sweep between 7 and 50 Hz, repeated over a minimum of 3 hours. This ensures that the internal components, the cooling lines, the bus bars, the cell connections, don't fatigue or crack after months of driving over rugged, uneven construction sites.
Okay, now if we look eastward, China often sets even more stringent regulatory benchmarks. What does their national standard, GB 380.301/2025, require that goes beyond that 5-minute escape window?
China's GB 38031/2025 imposes what is probably one of the world's strictest thermal safety requirements. The no fire, no explosion mandate must be sustained for a full 2 hours following the detection of a single-cell thermal event.
2 hours. That moves the requirement from just a safe escape window to near total containment of the failure event itself.
It demands significantly more conservative engineering. To achieve a 2-hour containment, manufacturers have to prioritize thermally stable cell chemistries like lithium iron phosphate, LFP, over higher energy density NMC cells, and they have to integrate substantial internal structural barriers.
So it changes the very design of the battery.
It fundamentally impacts battery material selection and how you allocate your safety factors.
And considering the daily operations of a cement mixer, Chinese regulations also put a big emphasis on environmental resistance, specifically waterproofing.
Absolutely vital. A mixer gets high pressure hosed down multiple times a day to stop concrete from setting on the chassis.
Right.
Chinese regulations require whole vehicle waterproofing tests, simulating driving through standing water and surviving extremely high pressure, high temperature cleaning jets. Every single high voltage component, the motor, the inverter, and especially the battery pack, must reliably achieve an IP67 or, ideally, an IP69K ingress protection rating. Failure here means an instant short circuit.
Shifting to North America, you have FMVSS 305A, which extends electrical safety to heavy-duty trucks. While it's focused on crash safety, what's the crucial requirement for the manufacturer when it comes to post-incident management?
FMVSS 305A, and specifically Part 561, mandates the creation and submission of standardized emergency response information.
For first responders.
For first responders, this is critical because even after a collision, the battery holds a huge amount of stranded energy. The documentation has to clearly instruct firefighters and paramedics how to safely disable the high-voltage system, where the manual service disconnects are, and how to verify that the high-voltage bus is de-energized to prevent lethal shock risks during an extrication. It forces us to design for the safety of the entire external chain.
Let's move to electromagnetic compatibility, or EMC, which is governed by ECE R10.07. The high-speed switching of the 400-volt inverter is basically a controlled noise generator. How do you stop that electrical interference from disrupting the sensitive 24-volt control network?
This is a constant battle between power and precision. The 400-volt switching creates both radiated disturbances, RFI, and conducted disturbances that can propagate through the wiring harness. If that noise corrupts the CAN-FD data buses,
The communication lines for the SCU.
the truck could experience anything from a minor sensor glitch to a critical system shutdown while driving.
So what does the testing setup for something so dynamic even look like?
EMC testing under R10 has to take place in shielded anechoic chambers, and we have to monitor the vehicle under 2 primary operational modes.
Okay.
First is normal mode. We run the truck dynamically, simulating high torque acceleration and high load mixing, monitoring the conducted emissions to make sure the inverter noise is contained. And second, if the truck is a plug-in, RESS charging mode.
Right, when it's connected to the grid.
We have to test the harmonics and flicker generated when the truck is plugged in to ensure it doesn't pollute the public electrical supply. The latest revision of R10 also extends radiated immunity testing all the way up to 6 gigahertz.
So you have to prove that your truck doesn't cause noise and that external noise doesn't interfere with your truck's brain.
That's it, exactly. And we use a few key strategies to mitigate it.
Such as?
Careful cable routing is a big one, separating high voltage from low voltage lines. Shielding is another, using specialized braided metallic sheathing. And finally, filtering, integrating common mode chokes and specialized filters on the inverters to suppress the noise at the source.
Okay, finally, let's detail the absolute physical and electrical isolation requirements. This is the last line of defense against electrocution.
This safety layer is entirely dedicated to protecting personnel. There are 3 non-negotiable standards. The first is the Insulation Monitoring Device, or IMD.
Which is always on.
It's constantly active, measuring the resistance between the high-voltage bus and the chassis ground. For a DC system, if that resistance falls below a critical threshold of 100 ohms per volt, which means your insulation is failing, the IMD triggers an immediate alarm and commands a system shutdown.
And why is that specific resistance value so important?
Because a failure below that level means the vehicle's chassis could become energized with potentially lethal current if a person were to touch it while standing on the ground.
Okay, second is the high voltage interlock loop, the HVIL, which provides redundancy.
The HVIL is a dedicated 24-volt low-current safety loop that physically snakes through every single access point of the high-voltage system, every connector, every panel, every hatch. It's basically a tripwire.
So if a mechanic opens something, they shouldn't.
If that 24-volt circuit is broken, the physical loss of that low-voltage signal instantaneously triggers the contactors to open, reducing the residual high voltage to a safe level, under 60 volts DC within 1 second. It's a hardwired safety interlock that completely bypasses software control.
And lastly, Equipotential grounding.
This is passive, but it's essential. All the exposed conductive housings of the 400-volt components, the motor shell, the inverter case, the battery enclosure, must be physically and reliably connected to the chassis with robust grounding straps.
And you have to test that connection.
We rigorously measure it. The resistance between any of those housings in the chassis must be maintained below 100 milliamps. That's 0.1 ohms. This ensures that if an insulation failure happens internally, the fault current flows safely to ground instead of energizing the chassis.
We've established that the ePTO system's ability to shut down the diesel engine on site is a massive efficiency boost, but it's also a powerful commercial advantage defined by noise reduction standards. So tell us more about this silent revolution and the value proposition of PIEC certification.
Achieving PIEC, which is the Quiet Truck Certification Standard, is a significant ROI driver for these fleets.
How so?
Well, construction sites in dense urban centers are often restricted from operating outside of standard business hours because of noise ordinances. A traditional diesel mixer is operating at 90 to 100 decibels.
Which is loud enough to cause hearing damage and generate a lot of complaints.
Exactly. PIEC compliance requires limiting the noise output during loading, unloading, and mixing to just 72 dBA at 7.5 meters.
That reduction is transformative. It allows a business to operate in the early morning or late at night, effectively doubling its potential delivery window.
Precisely. The ability to perform profitable nighttime urban deliveries, which often carry premium rates, fundamentally changes the total cost of ownership calculation for the hybrid mixer.
Yeah.
But this revolutionary silence creates a necessary trade-off.
The acoustic vehicle alerting system, or AVAS,
You solve the noise problem, and then the law mandates you add sound back in for safety.
it's a regulatory paradox.
It is. ECE R138 mandates AVAS compliance. Because the electric drive's nearly silent at low speeds, up to 20 kilometers per hour, the vehicle poses a real hazard to vulnerable road users.
Pedestrians, cyclists.
Pedestrians, cyclists, and the visually impaired. So the truck has to emit a synthetic, audible sound. Typically, it's a frequency sweep that shifts in pitch relative to speed, just to alert people nearby of its presence and its direction of travel.
So you're replacing the natural, loud soundscape of a diesel with a precisely regulated synthetic one.
You are.
Beyond the noise, this electrification introduces a whole new layer of intelligence. We're now seeing the ePTO motor itself being used as a high-precision sensor, leading to something called the digital slump meter. Explain the physics behind this.
This is one of the most exciting commercial applications of the high-voltage architecture. The consistency or slump of concrete is absolutely critical.
Right, if it's too wet or too dry, it's useless.
If it's too wet, it compromises structural integrity. If it's too dry, it's impossible to pour. In a traditional system, measuring slump meant stopping the truck and doing a manual cone test, which is time-consuming and prone to human error.
But the ePTO motor, because it's a high-precision PMSM, is constantly reporting on its own load conditions.
Exactly. The torque required to rotate the drum at a constant speed is directly proportional to the concrete's viscosity and its homogeneity. If the concrete starts to dry out or segregate, the motor current draw and the required torque increase dramatically.
And the SCU can read that signal.
The SCU filters this electrical signature, it removes the noise from sloshing, and it calculates a real-time, highly accurate virtual slump meter. This data is then displayed to the driver, alerting them immediately if the mixture's consistency deviates from the required spec during transit.
So this transforms the truck into an intelligent concrete management terminal. It allows for quality control checks that were previously impossible. Does the SCU integrate specific safety logic based on that real-time torque feedback?
It creates powerful predictive and protective logic. The SCU will implement anti-segregation logic, ensuring that even during long idle periods, the drum maintains a minimum rotation of 2 to 6 RPM to prevent the heavy aggregate from settling.
And the rocking mode we discussed earlier is also triggered by this data.
Precisely. The SCU's primary protective function is monitoring for an impending stall. If that torque measurement suddenly spikes, indicating the concrete is starting to seize, the SCU can automatically initiate the rocking mode, that dynamic reversal of the motor, before the driver even notices there's a problem.
So it saves the motor and the load.
It saves the electric motor from a stall, it protects the integrity of the drivetrain, and critically, it saves the load. It proves the massive commercial value of embedding high-precision electrical feedback into these industrial processes.
Okay, we've broken down the architecture, the rigorous V-model validation, and the non-negotiable regulatory landscape. To complete our top-tier consultancy framework, we have to define the final authoritative engineering outputs. What are the key deliverables that certify the system is safe, compliant, and ready for mass market release?
The output is formalized in a suite of 3 critical documents. These deliverables are the final authority, the proof that every single requirement, from safety to performance, has been met and verified.
Let's start with deliverable 0701, the DVP&R, the Design Verification Plan and Report. This is essentially the Bible of testing for this project, isn't it?
It is. It's the comprehensive, structured document that guides and then reports on every single test performed to verify the requirements of the 24-volt, 400-volt platform. The DVP&R links the initial design requirements directly to a successful physical or virtual test result.
And for a hybrid mixer, the mechanical integrity section of this report must be incredibly detailed.
Exceptionally detailed.
What unique mechanical challenges must the DVP&R validate that are specific to a high-voltage system mounted on a flexible, twisting truck chassis?
The key challenge is what we call kinematic mounting validation of the battery pack. A traditional highway truck chassis is relatively stiff, but a vocational truck chassis is designed to twist and articulate significantly when you're navigating a rough construction site.
So you can't just bolt the battery down rigidly.
You can't.
Yeah.
Its mounts must be kinematically designed, often using specialized elastomer isolators and pivot points, to decouple the battery structure from the chassis twist and flex. The DVP&R must verify, through structural testing and simulation, that the pack mounting prevents internal damage or electrical shorts caused by excessive strain.
And you also have to verify the extreme environmental robustness, that constant assault of high-pressure water.
Exactly. The DVP&R has to confirm the achievement of stringent environmental robustness standards. All high-voltage components, battery packs, inverters, motors, junction boxes, they all must achieve IP69K ratings.
Which is the highest rating.
It certifies that the equipment can successfully withstand high-pressure, high-temperature water jets, which is a daily reality for these mixers. The report documents the successful pressure wash tests, proving the integrity of all the seals and gaskets.
And furthermore, the DVP&R must verify the functional safety mechanisms as defined by standards like ISO 26262.
Yes. The DVP&R proves that the drum drive system, which can potentially cause severe injury from unintended rotation, achieves high automotive safety integrity levels. We're targeting ASIL C or D.
And how do you prove that?
This involves verifying the fail-safe mechanisms, like the safe torque off function, ensuring that if a fault is detected, the motor is electrically prevented from generating any torque, eliminating the risk of accidental rotation during maintenance.
Okay, moving to deliverable 0702, the safety certification checklist. This is the compliance matrix, the proof of legal readiness for market deployment.
This is a pass-fail document that dictates market access. It is the final check against that fragmented global safety landscape we talked about.
So you're checking off all the regulations.
The checklist verifies, line by line, full compliance with the most stringent requirements. ECE R100 Rev 3, China's GB 38031, ECE R10 for EMC, and crucially, it verifies all the visual and physical safety markers.
Give us those non-negotiable physical requirements.
They include the mandated standards for color coding. All high-voltage cables must be visibly jacketed in bright orange.
No exceptions.
Warning decals must be placed conspicuously at all access points. And the checklist must contain the final measured results, proving that the equipotential bonding resistance between every metallic conductive housing and the chassis is less than 0.1 ohms.
100 milliohms.
If the team cannot prove that specific, extremely low resistance value, the vehicle fails type approval, period. The checklist is the gatekeeper for mass production.
Finally, we turn to deliverable 0703, the performance analysis report. This is where the engineering investment is justified by commercial quantification, the total cost of ownership analysis.
This report answers the client's ultimate question. Does this complex hybrid architecture generate a positive return on investment? The critical KPIs start with the fuel saving rate.
Okay.
We have to compare the verified operational efficiency of our P2 hybrid plus ePTO system against the standard diesel hydraulic baseline over a representative duty cycle. The verified rate has to consistently meet or exceed our internal target, which is typically greater than 25%.
And the TCO analysis has to extend beyond just the fuel saved.
Absolutely. The total cost of ownership calculation is a comprehensive life cycle costing projection. It has to include the reduced maintenance on the diesel engine because it's idling less, the near elimination of maintenance on complex hydraulic systems, no more pumps, hoses, fluid changes, and the projected battery cycle life and degradation over a 10-year lifespan.
Okay. The last key metric in this report has to address the quality of the operator's experience. The NVH profile noise, vibration, and harshness.
The NVH profile is crucial. While we quantify the massive external noise reduction that lets us achieve PIE compliance, we also have to address the new internal noise problems introduced by electrification.
Right.
The primary culprit is what's often called the internal 48th order whine.
A 48th order whine.
It's this high-frequency, sometimes headache-inducing noise caused by the interaction between the high-speed switching frequency of the 400-volt inverter and the geometric design of the motor's stator slots.
So you replace the loud, low-frequency roar of diesel with an annoying, high-frequency internal hum. How do you mitigate that?
The performance analysis report includes a fast Fourier transform, or FFT analysis, which links electrical switching frequencies directly to audible noise levels in the cab. The mitigation strategies include implementing sophisticated noise-shaping algorithms in the inverter software to shift the switching frequency out of the human hearing range, or physically integrating optimized acoustic damping materials around the motor and inverter. We have to prove the cab environment stays comfortable for the operator.
This deep dive has just illustrated the immense engineering commitment that's required to bring a vehicle like the hybrid cement mixer to market. It's a journey that starts with the P2 hybrid and ePTO, integrates a very delicate 24-volt, 400-volt architecture, and then subjects the entire system to a relentless validation process defined by that V model.
And success wasn't about just adding a battery. It was about defining and adhering to a rigorous framework. From virtually modeling the chaotic sloshing of concrete to injecting potentially lethal insulation faults in a dedicated HL testbed. And finally, proving compliance with those global standards like ECE R100's requirement for a 5-minute warning and China's mandate for 2 hours of no fire, no explosion.
The ultimate achievement here is transforming a traditional mechanical workhorse, which was defined by fuel waste and noise, into a highly intelligent, data-driven machine. It's capable of silent urban operation, thanks to PIEX certification, and it now provides real-time quality assurance through the digital slump meter, all verified and documented in those critical engineering deliverables like the DVPNR.
This shift proves definitively that the future of heavy engineering is defined by software control and meticulous safety adherence. The engineering roadmap is the ultimate authority, and it transforms operational efficiency and market viability on a global scale.
So we'll leave you with this final, provocative thought. If the supervisory control unit can successfully use the ePTO motor's electrical signature to measure and manage the complex, unpredictable viscosity of concrete in real time, effectively automating quality control in the harshest industrial environment, what other seemingly simple, material-intensive industrial processes, from mixing construction polymers to continuous mining processes, are about to be completely revolutionized by embedding high-precision electric motors as virtual real-time sensors? What will the fully autonomous, intelligent, and silent construction or mining site of tomorrow actually look like?